Today we are going to derive a significant number of the derivative formulas that we're going to learn throughout the rest of the semester, including all of the trig derivatives using our trig limits. Okay, so the first question I have, let's keep this fairly simple. Let's consider f of x is x squared and g of x is, how about 4x cubed plus 3. Let's start with something simple like this. What is f of x times g of x? If we just multiply these out, what would we get? That should be fairly simple.
4x to the 5th plus 3x squared.
Beautiful. Now, I want to differentiate. The question came up the other day about parentheses and brackets and things like that. This is when I would use brackets just because it's easier to read. Is it okay to use parentheses here? Yeah, if you're doing this on a calculator, you don't have any choice. I want to differentiate this product. We learned how to do this last day. Can you do this without doing really any work? Can you go right to the answer?
20x to the 4th plus 6x.
Beautiful. Okay. Now let's go back over to here. What is f prime of x? And by the way, this is when you'd use prime notation, because I didn't use the letter y anywhere in here. I used f of x. So f prime of x would represent its derivative.
2x.
And what's g prime of x?
12x squared plus
And because that would give me a 0. You agree? So obviously, this is equal to 2x times 12x squared, isn't it? Houston, we have a problem. I just took the derivative of the product, and you're telling me it's not the product of the derivatives? But isn't that a limit rule? Because we know the sum of the limits and the limit of the sum, we know the scalar multiple, and then we have the product, the quotient, we have the composition. And I said only the sum and scalar multiples limit rules apply to other things. We just took the derivative of a product. Is it fairly easy to see that it is not the product of derivatives? Yeah. In fact, in general, this is not equal to the product of the derivatives. If it were, boy, life would be so much simpler. It's never going to be true. That one's a big fail. But I need this. We're going to be multiplying functions all the time. In fact, before we're done today, we're going to multiply functions times trig functions and have to do derivatives of products. And, well, we need to establish a rule for this. We need a formula that works. And I've just demonstrated that differentiating and then multiplying the results is not going to work. So, here's what we're going to do. I want to, for any two functions, f and g, I want to differentiate f of x and g of x. And we're going to start with the definition of the derivative, because that's the only way we're going to get this. And we're going to manipulate those limits until we get an answer. So this is going to be the limit as delta x approaches 0 of. Now, if it helps you, think of this as one function. And so what I need is this function evaluated at x plus delta x, which would be the equivalent of evaluating each of these. Okay, then minus f of x times g of x all over delta x. Okay, you with me on that one? So this is the derivative of the product in limit form. Now, does that help me at all? Writing it like that? Does this help me at all if I want to do that? Well, I can't evaluate, I can't factor that. That is the answer, but it's kind of a dead end. But I'm going to show you something. I'm going to show you an algebraic trick that I do all the time. Okay? All of you learned how to do long division of polynomials. All of you learned how to do synthetic division of polynomials when it applies. I'm going to do a simple problem. Okay? let's suppose I wanted to do the following. Let's say I had x squared, how about plus 3 over x minus 1. Well, actually, yeah, I want to do this. I want to use synthetic or long division to do this. So let's start by doing long division first. So I have x minus 1 into x squared plus 0x plus 3. You guys remember this? So we'd say x into x squared, x times x is x squared, x times negative 1 is negative x. X squared. And then I subtract the quantity. And that would leave me with x plus 3. I'm sorry, there should only be an x there, my bad. Then x goes into x one time. 1 times x minus 1. And what am I left with here? 4. So I'd write the answer as x plus 1 plus 4 over x minus 1. That's what we all learned as algebra babies. But synthetic division, when it can be used, it's usually way, way simpler. Synthetic division, the only limitation was I have to have the same variable and my denominator needs to be linear. I do have that. So with synthetic, the first thing we did was identify the root, which in this case is positive 1. Then I write all the coefficients in descending order. 1, 0, 3, because there's no x term. Remember what you did now? Multiply, add, add. That's my remainder term, my constant term, my linear term, same answer. Way simpler. Okay? Is there an easier way to do this? Oh, there's a much easier way. I show people this, and I actually will use this, but that's not what I do most of the time. I find it much easier to manipulate this in such a way that I can do this without doing any work. What if my numerator were this? That would be wonderful because this factors as x plus 1, x minus 1, doesn't it? We all know that. I would love it if my numerator were that. If my numerator were x squared minus 1, then I could just cancel the x minus 1s and I'd be done. But my numerator isn't x squared minus 1, is it? Yet. Is that legal? To change 3 into negative 1 plus 4?
Yeah.
And then what am I going to do? I'm done in the next step. This is how I've always done it. If you add and subtract the same quantity to a numerator of a quotient, first of all, it's always legal. There's no exception. But what you'll find is most of the time when you're doing long or synthetic, you can get the answer in one step without doing any work at all. If the degree difference isn't too great. If the degree difference is really great between top and bottom, no, then long or synthetic is probably safer. So let's do another one, because a lot of people don't realize how simple this can be. I want to do x over x plus 2. I can do long division, that will take me not very long. I can do synthetic, that won't take me very long. A number of years ago, I had students, they would call this Brown division, because this is how I do it. I rarely use long or synthetic. I do use them. 99% of the time, I'm lazier than that. I go like this. That's the answer, and it took me all of one step. This is what I do pretty much always, because it's easier, and I'm lazy. If you add and subtract the same quantity, so why am I showing you this? Because it's the only way I can do this problem, is to add and subtract the same term to the numerator, but it's got to be the right term. It's got to be the appropriate term. But if I add and subtract the same term to the numerator, I can then pull it apart. You got it? Much the same way I did here, because x plus 2 over x plus 2, that's 1. Minus 2 over x plus 2, and there's my answer. Okay? Now, I'm showing you when it's simple. But what if it's something big and icky and nasty like that guy? Well, here's what we're going to do. We're going to add and subtract the same term to the numerator. So I'm going to take this term and move it way over here. Now, the term I'm going to add and subtract, I'm going to add and subtract. Okay, do this. Is that legal?
Mm-hmm.
Is it helpful? Well, you know, if I break this up into two quotients, I might be able to apply limit rules that I know to the new quotients, because we know the limit of a sum is the sum of the limits. I haven't done any calculus yet. I just added and subtracted the same quantity to the numerator. That's always legal, because I haven't changed the value of the quotient at all. What if I now do this, like this? So I have f of x plus delta x times g of x plus delta x minus f of x times g of x plus delta x, and all over f of x, or excuse me, all over delta x, plus then what have we got? We've got f of x, g of x plus delta x, minus f of x, g of x. There we go. Stare at that for a minute. If I cover up the words limit, okay? If I cover up the word limit, is the first thing equal? Yeah, because I added and subtracted to the numerator. I have a bunch of stuff in the numerator. I pulled it apart into two separate quotients. We know that's legal. Now look at each individual quotient. Do I have a common factor in each one? Do I have a common factor? Well, here I'd have that in common, and here I'd have that in common. So let's see what we get. I know the limit of a product is the product of the limits, so I want to factor that term out. And so if I write that as, let me do that first, g of x plus delta x, all by itself, because I'm factoring just that term out, no denominator. Now let's leave what's left. Is that correct? I factored this out completely. I got that. Now, how about on the other side? What if I factor out the f of x? Again, if I cover up the word limit, is my algebra sound? Are all of those things equal just as algebraic quantities, as quotients? The answer is yes. If I take the word limit out of there and I multiply the f, it distributes back into the numerator. This would distribute back into the numerator. Can I give the answer now? As delta x approaches 0, what's happening to that? It's not a quotient. Isn't it just becoming g of x? What do you think?
Yeah.
Is delta x, that's just g of x. And this one's even easier. There's no delta x's there. As delta x approaches 0, what's happening to f of x? It stays f of x? Yeah. Oh, that was easy enough. All right, I'm halfway done. I've seen this movie before. G of x plus delta x minus g of x over delta x as delta x approaches 0. Isn't that the definition of, it's called the definition of the derivative, so what is it? G prime of x? Yes? Well, then what would that make this? F prime of x. Huh. Now, I'm going to write it, I'm going to switch the order of terms because it's easier to remember in this form. It doesn't matter. It doesn't matter. But what did we just come up with? We just came up with the derivative of this is f of x times g prime of x plus g of x times f prime of x. Whoa. And we have a very clever name for this. Now I always remind people, in mathematics, the theorem that does this is usually called the theorem that does this theorem. Probably the most important formula in all of human history, the one that's used by far the most often. You remember this from algebra. I'm giving you a point, and I'm giving you a slope. What do we call that? The point slope formula. It's 3,000 years old, and that was the best we could do. I've been rallying all these years trying to get a cool name for that, you know. I don't know, just like I have a titanium calculator. Just, you know, the formula that if you have a point and a slope, it's called the point slope formula. That's it. That's the best we could do. In almost every aspect of mathematics, we name the formula after the thing. So the rule for taking derivatives of products, we have a really clever name for this formula. It's called the product rule. Yeah. We couldn't come up with a cooler name than that, but it's easy to remember. When you hear the term product rule in mathematics, it refers to this. When I'm taking the derivative of a product, it is not the product of the derivatives. It's a bit more complicated. But there's no part of the process. Now, the first example that I did a little while ago, I said, I think I did x, what was the other one again? It was 4x cubed. The one we just started plus 3. F prime of x, we agreed, is 2x. G prime of x is 12x squared. Now, if I wanted you to multiply two polynomials out together, no, it's way faster to multiply the polynomials and then differentiate the result. That's always going to be faster. The product rule, the idea is I couldn't multiply these things out. It's too complicated. Maybe one of them's a trig function. Maybe one of them's a logarithm. In other words, things that can't be squished together. That's what we're primarily going to see with this. But let's go back to the example we started with. Because when we did this a moment ago, we said f of x times g of x was 4x to the 5th plus 3x squared. Therefore, the derivative of this we saw was 20x to the 4th plus 6x. We just did that a moment ago. Now I want to apply the product rule. It's not the most efficient way of doing it, but it is what it is. So according to the product rule, the answer to my question should be f times g prime plus g times f prime. Okay? F of x, g prime of x, g of x, f prime of x. And what does this give us? 12x to the 4th plus 8x to the 4th plus 6x, which is in fact 20x to the 4th plus 6x. Crowd goes wild. Well, obviously, the one on the left is a little more efficient because I was multiplying polynomials. But in general, the product rule will always get us to our goal. So the product rule is actually pretty simple to apply in general. I'm taking the derivative of a product that I can't multiply out. For example, what if f of x is x squared, but g of x is tangent of x? Right, I can't squish those together as one thing. So that's when we would actually use this. Okay? Any question on that? All right? I said that the limit of a sum is the sum of the limits. We've proved now that derivative of a product is the product of derivatives. We know that the limit of a scalar multiple is the scalar multiple of the limit. We proved that the derivative of a scalar multiple is the scalar multiple of the derivative. But now the limit of a product equals the product of the limits does not apply to the derivative, does it? It's a little more complicated. So I think it's safe to say it won't work for quotients either, will it? If it doesn't work for products, it's probably not working for quotients. So now we want to do this one. I want to take the derivative of the quotient. Anybody got a cool, clever name that we're going to call our result? Quotient rule. Quotient rule, yeah. we got to work on this, right? We're gonna take, we're gonna take names and suggestions and present it to the World Math Council to see, can we come up with cooler names for these really, really important formulas? Because these names are just too boring. All right. This one here is a little bit icky. Now, one of the things we really truly like about the product rule, it's a sum of two products. Addition and multiplication are both commutative. So does it even matter what order I did the things in? I said f times g prime. Could I have said g prime times f?
Mm-hmm.
I said f g prime plus g f prime. Could I have done the summation in reverse? Yeah. Product rule is very forgiving. I'm multiplying two things and I'm adding them. The order isn't going to change anything. But it turns out with a quotient, order does matter because quotients are not commutative. Differences are not commutative. So this actually is a little more important that I get the order perfect. All right, so we want to do f of x plus delta x over g of x plus delta x minus f of x over g of x all over delta x. Now, ultimately, I'm going to add and subtract to the numerator again, but not yet. That numerator is just too nasty. I have quotients within my quotient. So I showed you a shortcut last week. I would like to write this as, first of all, just one quotient, not multiple quotients within the quotient. We did a problem very similar to this last week, if you remember. For me to make this into exactly one quotient, first of all, what am I going to multiply numerator and denominator by? So the product of those two terms. Because those two denominators are different, I'm going to multiply top and bottom by those two denominators. Now they'll be gone from the top, but they'll show up in the bottom, won't they? So what will my new numerator, when I multiply by the product, I'm going to get that times g, and I'm going to get that times g of x plus delta x. And then they're also going to show up on the bottom. All right. Wow. It's kind of scary looking, isn't it? Well, I mean, don't worry about the bottom. The top looks almost like it did in the last problem, doesn't it? Well, it turns out in this case, this one's even easier in terms of my choice. I am going to add and subtract to my numerator. I'm going to add and subtract the term f of x times g of x. I'm going to add and subtract it. Okay? And when I do that, I'll do the subtract first, followed by the add. This will become all right, so I'm going to have f of x plus delta x, g of x, minus f of x, g of x, plus f of x, g of x. I said we're going to add and subtract it. And then finally, minus f of x, g of x plus delta x. All over delta x, g of x plus delta x, g of x. Okay. Now, the delta x is the problem, child. Do you agree? Delta x is approaching 0. Neither one of these are approaching 0. They're not a problem. It's the delta x that's the problem. So, equal, not equal. One person? There's a large cash prize for the correct answer. So far, you're the only, these are equal.
Yeah.
Because they're both equal to A over B times C. If I have something of this form, I can write like that. I can write it like that. Agreed? Do I have something of this form right now?
Yes.
Yeah, but I want the g's out of the way. So I want to take the g's out of the problem. Check this out. I'm just using some simple algebra. I know it's a lot of writing. Now, I want you to stare at this for a minute. Remember, if I cover up the word limit, is it still true? I just took something of this form and I rewrote it as one of these two, didn't I? So I took this and put it in a new denominator by itself. Do you know why? Because that's easy. I can do that right now. As delta x goes to 0, doesn't this just become g of x times g of x? This quantity? Yeah. So we're going to keep that one out of the way. Now look at the stuff on top. If I do exactly what I did with the product rule and I pull it apart as to two different quotients, we'll be able to finish this in no time at all. So on top, I'm going to make it this, and I'm going to make it this. Okay? So on top I've got the limit as delta x goes to 0 of f of x plus delta x g of x minus f of x g of x all over delta x. And by the way, I'm just going to go ahead and evaluate the bottom. The bottom limit I'm just going to go ahead and do now. I'm lazy, I don't want to keep writing limit. Again, there's no quotient here, so I can have delta x go to 0 right there. Now, I want to factor out an f of x. If I factor out the f of x, I'm going to have g minus gx plus delta x. Does that feel backwards to you? Don't I want the x plus delta x term to come first? It's coming second. How do I fix that? I have a difference. I have a minus b, and I really would like it to read b minus a. How do I do that? Instead of, how about factor? Right idea. Can I do that?
No.
I need g of x plus delta x to be minus g of x. So instead of factoring out f of x, let's factor out negative f of x. Okay? Then I can write it like this. Minus the limit, or negative 1. Let's just keep it simple. I'm going to factor out negative 1. And then it will be f of x, g of x plus delta x minus f of x, g of x, all over delta x. That's 0, sorry. Oh, this is looking good. This is looking just like the last problem, isn't it? I can factor one term out and literally be done. It's not quite the form of a derivative yet because my numerator, I got to factor this out. And on my second term, I got to factor this guy out. But when I do that, I'll be all done. I'll be ready to evaluate. There is no shortcut. There's no way to get this formula without doing what we did, but we're almost finished. Move this up higher so you can see it. So if I factor out the g of x, so again, limit of a product is the product of the limits. And what does that give us? That gives delta x goes to 0, and I'm going to write it in this order. I'll do the g of x first, and then the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. Because the g of x I factored out. It's not in a quotient anymore. Minus the limit as delta x goes to 0 of f of x times the limit as delta x goes to 0 of g of x plus delta x minus g of x all over delta x. Oops, sorry. All over delta x, and then the whole thing was over g of x quantity squared. We're done. We can now evaluate each of these limits because everything here is a standalone. Well, this is the easy one. As delta x goes to 0, g of x just stays g of x. It's not very exciting. Well, what is this? That's f prime of x exactly. As delta x goes to 0, what's happening to that? Just staying f of x. And what's that? That's g prime of x. Ooh, this one's a little more complicated, isn't it? Now, I have a difference of a product all in a quotient. Do you think the order matters here?
Yes.
Yeah, because if I get things out of order, it will change my answer, so I've got to get it right. So I have the derivative of the quotient. So in words, it's denominator times derivative of the numerator minus numerator times derivative of the denominator all over the square of the denominator. Yikes, that's a lot to remember. So I'm going to give you a little history. A lot of you guys aren't aware of just how much calculus you've had in your lives, ever since you were little kids. But a lot of it was softened, right? It was sort of watered down. So how do most people remember the right triangle trigonometry? Right triangle trigonometry.
Is that the special?
You guys all know this. So I always tell the story. I always start by telling the story. Back in I think it was in the 1800s, the largest measured tidal wave that ever took place. And there was an island, I believe it was in the South Pacific, there was an island called the island of Krakatoa. If you wanted to go visit that island today, could you? No, it's not there. It's literally been removed from the planet. It's underground, kind of like the lost city of Atlantis. But just like the Jurassic Park movies, remember there were two islands. The lost island of Krakatoa had a sister island called the island of Sokotoa. And most of you are familiar with the island of Sokotoa. It's kind of like the lost city of Atlantis. They did amazing mathematics without the use of technology. They could do right triangle trigonometry, all sorts of things. And it all had to do with how you spelled it. How do you spell the island of Sokotoa? I go on a limb and say almost everybody here, this is how you learned your right triangle trig, isn't it?
Yeah.
You go, oh, it's called a mnemonic device to help remember. Well, turns out you guys all remember the story of Snow White and the Seven Engineers, right? You remember that story, right? Well, okay, they was, nowadays to be politically correct, it was Snow White and the vertically challenged engineers, but they did calculus. They didn't work in a mine. No, they worked in a computer lab. They're kind of boring individuals. But every day they would sing the quotient rule on the way to work so they wouldn't forget it. Okay? And the easy way to remember the quotient rule just to make it easier, if I call my numerator hi and my denominator ho, then the quotient rule quite literally is ho and every day on the way to work they'd sing ho-dee hi minus hi-dee ho all over ho ho, and then they'd do the annoying whistling thing. But that's not the version you heard as kids. You heard the dumbed down version where they removed the derivative actually from the song, right? But you guys, if you think about it, yeah, those guys were doing calculus every single day and they would sing it. And you're laughing. Every calculus test I've ever given, at some point during the test I go, okay, write it out. So it's ho-dee hi minus hi-dee ho over ho ho. You're laughing now. Nope. It's going to be just as important as Sokotoa at some point. It's how people remember things. Now, in the long run, you'll remember it because you'll do it so often. But there's two places we make mistakes here. Again, because division and subtraction are not commutative. I can't reverse the order of the subtraction, and I can't get the other things wrong. I gotta get it in the right order. Oh, thank you for the question. So let's do this, because this is going to be used quite often, quite often. So we will write it out. I'll keep it relatively simple. I want to take the derivative of a simple rational function. So let's say we have 3x minus 4 over x squared plus 2. Now, there's nothing clever I can do with this. There's no longer synthetic division to perform because the numerator is a smaller degree. But I do want to take the derivative of this quotient. Now, there's no shortcut. I actually have to do this from beginning to end. So I'm going to write it out formally. It's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the square of the denominator. Okay? Have I actually done anything yet? No, I just wrote out what it is I'm going to do, but once I do it, it should clean up really nicely.
Can you cancel out the 2x plus the 2 squared plus 2 on top
Well,
of the...
if I break this up into two quotients, I could. But because it's...
Right.
So it's kind of like you're asking the question, if I have a minus b over a, can I cancel the a's? No, but I can split the quotient up and cancel it in one.